Good morning, ladies and gentlemen. It is 11, but in Morocco and 12 in Germany. And I would like to introduce Professor Dr. Thomas Hannappel. He's in Germany, in Illinois University of Technology. He can maybe give more detail on this institute. And he's working on solar. He's very well known in semiconductor tandem solar cell first, and now he's working very much on the production of or toward production of green hydrogen using 3,5 compound and silicon as well electrode. I think he's a full professor at Illinois University of Technology, Institute of Physics. His research focused on efficient solar energy conversion, high performance optoelectronic materials, and critical interface. This means he worked on very much on fundamental problem of interface between semiconductor and a device. Before he was scientific director at CIS Research Institute, Erfurt, acting director at Helmholtz Center Berlin, where I met him and I know him. Even before he was head at the Hahn-Meitner Institute, because the Helmholtz Center was before Hahn-Meitner Institute, and the name have changed for some reason. He was also, and I believe he's still lecturer at Free University Berlin since 2005. In 2003-4, he conducted research on silicon 3,5 heterointerface at the National Renewable Energy Laboratory in the United States, and that is a very good team where now he's working very much, and it's a very successful work. He received his PhD from the Technical University Berlin with a study on photo-induced charge carrier dynamic. He performed on the Department of Physical Chemistry at Fries-Haber Institute as well. So he will tell us more about the subject, semiconductor tandem structure for efficient artificial leaves. It's a very hot topic. It's maybe the solution for green hydrogen in the future, we hope. And he's working with a very known institution like California Institute of Technology, what we call Caltech. And he will give us more in his talk. So the virtual floor is his floor today. And I want to thank him again for his kind acceptation to our invitation. Please go ahead. I will leave the screen for you, and you can use it. Thank you very much.
Yeah, thank you very much for the very kind introduction. And I'm again very glad to contribute to these efforts which are made in particular by you and in Morocco. And so this whole initiative I really appreciate a lot, and I'm always glad to contribute. Yes, and that's true. Today I would like to bring this topic further to you. The topic is artificial leaves. In other words, we would like to create solar fuels out of one of the first solar fuel is of course hydrogen, but there is also higher value fuels possible. So now I would like to show my laser pointer. I think you can see it now. Can you?
Yes.
Yes. And you can also see the presentation well. I hope if anything is bad, please just interrupt. Or if there's any questions, please interrupt. Okay. So that was also true. We are historically working on high performance materials, which are giving the opportunity for the bandgap engineering, the famous bandgap engineering, which was introduced in 2000 by the Nobel laureate Herbert Krömer, Alvarez, and Kilby. And this makes possible to have highest efficiencies in solar energy conversion, up to almost 50% with our world record solar cell, for example. We have shown this some years ago already. And also artificial photosynthesis is also possible by using tandems. I will show this also. And the whole challenge is highly interdisciplinary. This we need to see. It's physics, it's chemistry, it's everything. So, and also industry, of course, is very much interested in this topic since it's a very huge and hot topic. Green hydrogen, of course, is on the agenda of many political strategies, and not only scientifically, also, of course, for our society and for this planet. So this is a brief outline I would like to give. I would like to address the following points. How can we split water efficiently? I think this is a very fundamental question, of course. Very fundamental is also the so-called Shockley-Queisser limit, or the detailed balance principle, which gives us a limit how we can convert sunlight. I will get to this point briefly. Then we are talking about the huge field of semiconductors. Semiconductors are the materials which are suitable to absorb light and to convert this solar light into free energy, so that we can use it either to produce electric power, or in another step, like plants are doing, in chemical fuels, in a first step hydrogen, and in further steps also, for example, for converting CO2 in fuels. Then, of course, always in the society and everywhere, costs is that point which is decisive for being competitive. I will also address this in our strategy. And of course, then I will briefly go to the point of science. Science here is huge, and many points. Among all of this is how to look at it, how to see it. And this is the field of analysis and spectroscopy. Of course, I would like to appreciate all who have contributed to the work which we are doing. As I have shown before, I'm sorry I didn't say this explicitly here. You can see here our valuable partners, which is the Joint Center of Artificial Photosynthesis. Now it turned to ELISA, but in general, the Caltech, Harry Atwater, Francis Ohl, and then we are planning, I will also show this, a strategic initiative, collaborative research center with different partners. Among those, and our direct partner here is Technical University Darmstadt and Helmholtz Center Berlin, and Fritz Haber Institute, Max Planck Society. Also a historical, very important partner of us is Fraunhofer Institute of Solar Energy Systems. Okay, so just to show, since you addressed Ilmenau, this is always difficult. Ilmenau is a smaller site, a smaller town, but with a very good and very well equipped university. So you can see here Ilmenau is always directly underneath the label Germany. If you see the German map, so it's in the center of Germany, and very nicely at the north of the Thuringian forest, Thüringer Wald in German. It's really beautiful there. And what we also have already history in science already in the last but 1 century, 1894 it was founded, the Technicum, and then it developed very well, and the sites which we have right now are really brilliant. So it's a kind of model case how to realize a very good infrastructure for engineering, technology, and science. Yeah, I'm always showing more or less first. This is already now more than 17 years ago that the Nobel laureate Smalley was showing this list of humanity's problems, and the first problem here is and was energy. We are talking, of course, about renewable energy, sustainable energy. And if one thinks one can see easily that all the successive points, in particular water, food, environment, are also depending on clean fuels. So, or let's say in provision of energy, green energy. And this is absolutely the key point in the future where we all need to work for. And we have this fantastic energy source, 62.5 million watts per square meter, originating from this very nice star. And by concentration, we can bring back the power, which is here from the surface of the sun, emitted to the earth. And this is a fantastic point that we can use it very, very efficiently and for free. However, we don't use it so far, even though we only need a very small portion of it. Some few percent of the surface of the Sahara, for example, would already be suitable to provide energy for the whole planet very easily. So this is what we need. I'm sorry, 20 terawatts. This is what we need, and this is what we have, and this is easily it can easily be harvested from the sunlight. However, what we do is we are more or less doing really wrong treatment of our planet right now, and we are facing really in severe problems, as you all know. Climate change and many more things which are real dramatic problems which we are facing to right now. And the only very optimistic curve is this one, which shows us basically the cumulative installed capacity, so accumulated modules which are built in the past and today, and now we are almost at this point here. I think at the end of 2021, we are close to a terawatt installed capacity on this planet, which of course is, if we would proceed with this, and you can see this, already in about 10 years, we are really in the terawatt regime, and we can foresee that this all will be very huge. So we need to do this, but we can do this, and it will happen. The only question is how fast, and this is exactly what we need to do, and which we need to work on, and to, of course, support in any direction which we can. And what I see, just yesterday, I've seen this by looking quickly, and I've seen Morocco is really doing very well with many, many initiatives. I have seen that there's almost 0.5 gigawatt plan for PV, another power plant, and I'm really very happy to see this. This is really the model case. However, still, besides all these efforts, we need more. We need, of course, to think about the issue of storage, of system stabilization, of mobility, of course, of the whole clean and green energy cycles. And for this, we need solar fuels. This is, I would say, another key element which is necessary to proceed, and this shows us a picture which combines the issue of hydrogen in the center, as you can see here, which we can, of course, either produce differently or use differently. It, of course, is also supported by the electricity cycle via fuel cells, and also an element, as plants are doing, to produce higher value fuels like methanol or formic acid and so on, methane. And this is, of course, very challenging. It's called the holy grail of renewable energy research, solar fuels based on hydrogen. And there is two ways to do this. We can either produce electricity and then trying to drive a PV electrolyzer. This is the more established way, the more mature way right now to do this. And there is a second way, like the nature is doing it, like plants are doing this, leaves, natural photosynthesis. This is directly using sunlight via photoelectrochemical processes and directly producing fuels like hydrogen. And there is, of course, if you compare these two routes, you can, of course, have different arguments for back and forth. But the artificial leaf, of course, is the direct way, the king's way. It uses, in comparison to driving electrolyzers, lower current densities. It can use a larger spectrum of catalysts, which might be applicable here. Less precious catalysts. It's also thermodynamically and dynamically more favorable. There is no need for two different separate systems. We only have one artificial leaf. There is no electric circuitry. And of course, like photovoltaic, like solar cells, it's scalable randomly at will. This is some arguments. There is even more arguments. We can, if we compare this list, like, of course, the point that the heat normally is unfavorable for photovoltaics, but in this photoelectrochemical process, heat can accelerate the reactions. So, of course, the principal thought that I have just one part, one device which I can use, this is, of course, already a very good argument. And just to show this again, this is, for example, here. Can I show this? It doesn't work. No, it doesn't matter. What I'm showing here is that the hydrogen can be directly used at the surface. I'm sorry, used also, but it can be directly, it is directly produced at the surface, not via any kind of detour. This is, of course, very nice to realize. Okay, there is one point which is always discussed, and this is the point, can we exceed the Shockley-Queisser limit? Can we exceed the detailed balance limit of efficiency? I just want very briefly to comment on this. What does it mean? In a normal solar cell, in a normal photoabsorber, we have severe losses, huge losses. One loss, of course, is that we cannot absorb light which has lower energies than the bandgap. And this is a huge loss, of course. Another huge loss is, of course, that all photons which have higher energies than the bandgap of a semiconductor are immediately, in less than a picosecond, losing their energy down to the energy of the bandgap. And these two huge loss channels already, together with a few more, like, for example, Auger, recombination, lead to this limit that a normal photoabsorber can never produce higher efficiencies than 30%, around 30%. And the question is, can we change this? Is this wrong? And the brief answer is no, it cannot be changed since it's a physical limit. However, what can we change? We can change the boundary conditions of this limit. And this you can see here. I listed here the boundary conditions which lead to the detailed balance principle. This is that the sun, of course, has a certain temperature, that our planet has a certain temperature, that we are only regarding radiative recombination, that we have only one absorber, and that we completely absorb light. Each photon produces one charge carrier, or let's say two electron hole pairs, we call it. And also that we have ultra fast thermalization. But we can change this. We can change, in particular, the points that we have only one absorber. And this I would like to show very briefly. And briefly, you can see this here. In one absorber, normally, and this is very, very important, we have in equilibrium one electrochemical potential, the Fermi level. And after light absorption, after producing an electron hole concentration, we have two different electrochemical potentials. This is the free energy which we can use. This is extremely important to see. This depends on the charge carrier concentrations which we are producing by light absorption. And if we then compare this to the redox potentials of water, here you can see of hydrogen and oxygen, you can see that we need 1.23 electron volts, and then it can be reduced, even the voltage, by recombination processes in the material and in the or at the interfaces here, and this all degrades this voltage which we need. Finally, even in the best case, we see if we just use one absorber, we can only absorb a small portion of the solar spectrum, even if we do the best of everything. So how to deal with it, how to improve this? And this is the question which I raised. We cannot improve it by just using one absorber. So the answer is we need to use tandem structures. In a tandem structure, we can do both. We can produce enough free energy to split water, as you can see here. And secondly, we can exploit the solar spectrum much better. This you can see here. This is a very important point. And this leads us to the theoretical highest efficiencies which we could reach to split water. And this holds also true for other solar fuels like producing methane or formic acid or methanol or whatever. Yeah, we need to use tandems. This is the basic point I wanted to show here, extremely important. Then, of course, we also need to make sure that all the ingredients, all the different parts, like the two different absorber materials which we need, have, of course, very good optoelectronic properties. Yeah? One major property is that the diffusion length here is higher than the penetration depth of the light. This is a very important boundary condition which we also need to consider very strongly. And then we need more and more ingredients like charge separating contacts, which can be realized. They have been nicely described by Peter Würfel, for example, who wrote the book Physics of Solar Cells, a very, very good book. Can just suggest to study this. Then also we need tunnel junction, where Isaki got a Nobel Prize for the invention of the so-called tunnel junction. And then we have the perfect device, as you can see, with very good photoabsorbers, with very good charge selective contacts, and with a perfect tunnel junction here, where we have isoenergetic recombination. And if everything is perfect, we can reach highest efficiencies up to 25 or even higher solar to hydrogen efficiencies. And beyond this, of course, we need to study the catalytic activities. This is, of course, also a huge field which we need to work on. And besides this, of course, we need to work hard on the issue of stability, of corrosion, of the solid-liquid interface, of chemical passivation. And then you can see here a kind of perfect device structure which can be realized in this case by P5 semiconductors, where you can see the whole mechanism here for producing hydrogen and producing oxygen and exploiting the light very efficiently. Okay, that's what I wanted to show. In addition, you can see that even other solar fuels, like formic acid, methanol, and methane, and so on, are also in a very narrow range of free energy you need. This is, of course, much more complex process, since we have these processes, multi-charge carrier transitions, which we need to consider. So there's always more than one charge carrier involved in these reactions. And these chemical reactions, of course, need to be studied more thoroughly to directly address certain solar fuels. But one of the fuels which we have already successfully addressed is hydrogen and oxygen, splitting water. That's what I already have shown in the past. In 2018, we have realized Reflectance, and I think it's very important to see that we can achieve very high efficiencies. And a device which would have efficiencies in the range of 20%. This would, of course, be a competitive device. Of course, you need to compete with costs which are realistically for a solar fuel. We all know that this cannot be in ranges of $10 or so. So we need, of course, to get firstly to high efficiencies. Without high efficiencies, we also see this in photovoltaics. We could never be competitive. Even in photovoltaics, a solar cell below, let's say, 15% would never be competitive, even if it would be for free, due to the balance of system costs. And the balance of system costs, of course, will be higher for such photoelectrochemical cells, for such artificial leaves, compared to photovoltaics. And yeah, this I already showed. I'm sorry for this. I wanted to show this. You see a contour plot of the combination of the two subcells in such a tandem structure. You can see the bottom band gap, which is shown here on the x-axis, and the top band gap, which you can see on the y-axis. And if you combine both, for example, in the ranges of 1 eV and 1.7 eV or so, then we are here more or less in the bull's eye of the efficiencies. And if you now regard where we have been with our racket cell, this was not in the bull's eye, but also not so far away. And there is still space for improvement, but you can see already by, for example, using silicon, I show this later on again, we would be also close to the bull's eye. So the issue of costs I get now, what you can see here is where are we with regard to costs? For this very efficient cells, you all know that they are very expensive right now. Not only due to the ingredients, since the ingredients are not so expensive. We are not talking about platinum or iridium for the photoabsorbers. I'm right now talking about the photoabsorbers. This is a typical high efficiency P5 solar cell, which is normally grown by the so-called MOVPE technology. MOVPE is metal organic vapor phase epitaxy. It's also called metal organic chemical vapor deposition, MOCVD. And one of the important points here is, of course, that we use a very important, yes, also, but I wanted to say very expensive substrate. This very expensive substrate normally is out of a 3,5 material like gallium arsenide or germanium. And so this is, of course, a piece, one part of this cell, which should be replaced by a much cheaper one, which would be, for example, silicon. And that you can see here. If you see that the cell costs right now for such a high efficiency cell is way too expensive. So what we would need is, of course, to be much cheaper, like 2 orders of magnitudes. And then you can see that one huge step would be, of course, the replacement of the silicon. And there is, of course, many different screws which we can toggle to reduce these costs. In particular, the whole process of growth, the epitaxy. And of course, the back end of line, and so on. So there is ways to get to much cheaper costs. One more would be if we would also consider concentration of light, a low concentration, since we do not want to have very high current densities. However, this costs could be really further decreased much by exchanging the expensive substrate. This is one thing what we are working on, and which is not only important for artificial leaves, but also for many other applications, of course, also for solar cells, but for the whole optoelectronics, sensors, detectors, light emitting diodes, and so on. It would be a really big point to be able to grow C5s on silicon successfully. Successful means without high defect densities. This is already a point which has been addressed by the Nobel laureate Herbert Krömer. And by the way, he was writing an email to us some years ago from Santa Barbara. And we were kind of very glad, proud that he recognizes our work on this topic, the topic of C5 growth on silicon. And here you can see a kind of a roadmap, what you could do, many opportunities if you successfully combine C5s with silicon. Here on the left-hand side, you can see that it would perfectly, almost perfectly fit to the highest efficiencies to achieve for solar cells as well as for water splitting. And on the right-hand side, you can see that you have opportunities by using nitrogen diluted C5s, by quantum well structures, by metamorphic grown layers, and nanowire concepts. So I could talk long about this. This is a roadmap. We recently did some work to reduce the defect density considerably. In particular, at the past, there is much progress right now with growing C5s on silicon. There is a new world record which Fraunhofer ISE has published. We are strongly working together on this point, Fraunhofer ISE and us. So we established now a new nucleation route very recently, and we are sure that this gives new opportunities now to be even more successful. And we are close to the step that this technology will be the breakthrough for cheaper, high performance tandem structures. This is a gimmick to show this, what we exactly doing, and this is the general challenge which we have in science. How can we look at buried interfaces? This is exactly what we need to do. How can we see this? And for this, we have in our lab so-called in situ application. We call it Reflectance and Anisotropy spectroscopy. This is a little difficult to understand and to explain, since it's not intuitively understandable or not so well known, like, for example, electron spectroscopy for chemical analysis, XPS, and so on. But it's a very, very informative analysis method. And we employed this here and have seen the interface here. I could show this longer. I don't do this now. Just wanted to give an impression. So this addresses the point interfacial control in situ and operando spectroscopy. So we see again this device here and all the questions which we have, all the critical parts which are catalysts, the electrochemical processes, the charge carrier dynamics, the protection layers, the passivation, the photoabsorbers, the efficient charge separation, the structuring at the cathode and or anode, and the huge problem of understanding in general. And for this, we are right now trying to establish a so-called collaborative research center. In German, it's called Sonderforschungsbereich. It's a huge initiative with many partners, and this is meant to start in the beginning of 2023. This is our goal and target, and this would at least, or no, let's say it another way, this would target a time period until 2035, where we would really like to make the whole split from understanding to application, and to understand and explain artificial leaf structures, and to use for this to integrate multi-junction absorber catalysts. We have here these partners, which I have already shown before. Darmstadt University of Technology, together with Ilmenau, will apply for this, and having partners at TU Berlin and HZB, and so on. I already mentioned this. This is what we are addressing right now. It would, of course, be a good point to solve all the questions which I have already mentioned in my talk right now, of course, involving even more all available material classes. Here in my talk, I, of course, focused on the material classes which we are preparing in our lab. And we would also like to establish new lighthouse experimental sites, also using synchrotron facilities. Yeah, that's finally what I would like to say. It's a huge challenge, and we need to use, or we have the challenge to address very difficult questions. As I mentioned, catalysis, interfacial reactions at solid liquid, solid gas interfaces, difficult chemical environments, and difficult spectroscopic methods and challenges. So this is all meant. This is a spectrum of methods which we have in our lab, state-of-the-art preparation of photoabsorbers, in situ spectroscopy, combined with surface science, and also characterization of solid liquid interfaces in photoelectrochemical chambers. Of course, we also need quantitative ex situ methods. I didn't tell about a fantastic method, for example, which is electron channeling contrast imaging, which shows us basically the defects which we have in a very nice way on the mesoscopic scale. So hopefully I showed that we have these challenges for the artificial leaves, really difficult challenges. I hope I was not too fast and not too long. So you can ask, of course, all kinds of questions. I would be glad about this. Finally, of course, I would like to thank you and to thank many more partners than those which I have already mentioned. We have fantastic collaboration in the Czech Republic, in theoretical modeling, and also at Tokyo University with Professor Sugiyama, with different industry partners like very important Space Solar Power, which really appreciate our methods which we are applying. So we are really doing in our lab the split from more fundamental science to industrial application. That's it. Thank you very much. Are there any questions?
Thank you very much, Professor Thomas Hannappel. As we always do in our traditional open lecture, we give one summary in Arabic that for the Arab world, if you allowed me, Professor Hannappel, and then we go back to you and to the questions. So أستاذ سالم.
أهلا وسهلا بك Professor Ahmed, and thank you also for Professor Hannappel. I think yes, to go to the brief in Arabic.
Okay.
Yes.
So, Assalamu alaikum wa rahmatullahi ta'ala wa barakatuh. بسم الله الرحمن الرحيم. رب اشرح لي صدري ويسر لي أمري واحلل عقدة من لساني. أشكر الأستاذ الدكتور توماس هانابيل جامعة إلينوي للتكنولوجيا معهد الفيزياء أساسيات مواد الطاقة ألمانيا. الخلايا الشمسية الثلاثية المتجانسة المصنوعة من عناصر الصفين الثالث والخامس من الجدول الدوري معروفة بكفاءتها العالية جدا، ويتم تسريب عدة طبقات رقيقة من الميكرومتر من أشباه المواصلات المركبة من عناصر من على الأقل من المجموعتين الثالثة والخامسة في الجدول الدوري المعروف باسم الجدول الدوري لمندلييف، وهذا ما جاء به الأستاذ توماس هانابيل، والمنسوب للعالم الروسي ديمتري إيفانوفيتش مندلييف، وهو الذي وضع من ترتيب جدولي للعناصر الكيميائية ما يسمى الجدول الدوري أو النظام للعناصر الكيميائية، ويسمح هذا بالتنبؤ بمركبات كيميائية انطلاقا من التكوينات الإلكترونية لكل عنصر كيميائي يشكل المركب. وتوجد عدة طرق مختلفة لإنتاج الخلايا الشمسية من أشباه المواصلات انطلاقا من الصفين الثالث والخامس، تؤدي إلى كفاءات أعلى بكثير من خلايا السيليكون الشمسية، تحول الطاقة الشمسية إلى لإنتاج الكهرباء بنسبة مئوية تفوق 34%. الأستاذ توماس هانابيل تحدث عن ميتال أورجانيك كيميكال فيبر ديبوزيشن وغيرها. تطوير تقنيات ومعالجة المركبات 3-5 من مندلييف تيبل من الجدول الدوري لمندلييف أدى إلى صناعة الخلايا الشمسية من الجيل الثالث third generation، مكنت من تقديم كفاءة أعلى من الحد النظري لخلية السيليكون الشمسية. البحث والتطوير مكن من تصنيع الخلايا الشمسية الكهروضوئية لإنتاج الكهرباء بكفاءة عالية تزيد عن 40 نسبة مئوية. الأستاذ توماس تحدث عن 46% وأكثر. أيضا الجمع بين السيليكون والمركبات 3-5، خصوصا نمو هذه المركبات من الجدول الدوري محوريا على ركيزة السيليكون، مكن من تصنيع خلايا الشمسية كهروضوئية بكفاءة عالية، ويمكن أن تخفض سعر هذا النوع من الخلايا الشمسية، وكل هذا تحدث عنه الأستاذ هانابيل. من المهم الإشارة إلى أن هذه الأجهزة تعمل تحت الضوء، تخفض سعر هذا النوع من الخلايا الشمسية. من المهم الإشارة إلى أن هذه الأجهزة تعمل تحت الضوء المركز كما جاء به، وكما قال من الأحسن أن لا يكون مركزا جدا. أيضا يمكن تصميم الخلايا الشمسية عن شكل أقطاب كهروضوئية لإنتاج الهيدروجين الأخضر، وهذا هو الموضوع اليوم. وعلماء آخرون في ورقة وصفوا فيها توماس هانابيل، ثم نشر دليل على المفهوم من قبل الأستاذ بالإضافة إلى استكشاف الطيف الشمسي بكفاءة أعلى. استطاع الباحثون في الرسالة التي نظرنا إليها، وهي أظن في Journal of Environment، وهو عنده يعني impact factor أكثر، أظن أكثر من 20 أو 25 لا أتذكر. استطاع الباحثون في هذه الورقة تحويل الطاقة الشمسية إلى هيدروجين بكفاءة تقريبا 19%. نحن محظوظون لوجود البروفيسور توماس هانابيل، باحث ممتاز، زميل سابق في مركز هيلمولتز ببرلين، الآن أستاذ بجامعة إلميناو للتكنولوجيا ألمانيا، ورئيس مختبر متميز في التمثيل الضوئي الاصطناعي بتحويل الطاقة الشمسية إلى طاقة كيميائية، وهذا تقليد للتمثيل الضوئي الطبيعي للنباتات. شرح الأستاذ توماس هانابيل هذه العملية المعقدة وقدم أحدث ما توصلت إليه التقنية في تقليد الطبيعة والإنجازات في مؤسستي. وشكرا.
شكرا بروفيسور أحمد على هذا الملخص والتعريف باللغة العربية. Now let's go for the question and answer and comments session. Please, the floor for everyone who wants to ask or comment. Any questions? Who wants also to raise his hand to speak? It's allowed. Yes.
If there is no one, I have questions. Huh?
All right. So I think you will move ahead, Professor Ahmed.
Okay. Sorry. So one very complex question is what always I have discussed before with Professor Tribuch is the splitting of water is 4-electron process. This means you need 4 electrons at once, I guess, to split water. And I always wonder how to get this. If is it just a question to have enough electron on the surface, like concentrating light and having or there is a kinetic problem where even if you have a lot of electrons at the interface, you need something more, something else. No? And what is this something else exactly? Thank you.
Yeah. Of course, this is the most difficult question you are raising right now, since, of course, yes, the dynamics, what you are addressing, as well as, of course, potential losses, this is exactly what we need to study. You are exactly right, of course, at the reaction interface. So we have multi-electron hole transfer in the semiconductor, and in the photoabsorber we have different kinetics. The dynamics is completely different. And we need, of course, firstly, to say it from a physical view, from a view of physics, we have, of course, to prevent the non-radiative recombination processes, even if the velocity at the reaction interfaces, it is slower. So firstly, we need to make sure, of course, that the kinetics at the solid-liquid interface at the catalyst is fast, and that there is not, it's not slowed down by high overpotentials, by high barriers of the kinetics. And then we need to make sure that before is not the lowering of the electrochemical potentials of the Fermi levels. This could be either if we have interfacial defects. This can also be if the electronic alignment is bad. So the catalyst electronic level, for example, needs to be, of course, in the range where we have our electrochemical potential level. If this is very different, of course, then we have the potential of severe losses. So let's say of course, kinetics at the catalyst, the electronic alignment of catalyst redox potentials and the semiconductor device structure needs to be aligned perfectly. We need to prevent electron hole recombination, as well as, of course, losses maybe at the reaction interface. But this is all difficult. You know that this is described for a semiconductor by the Marcus Gehrig theory, and for metals also, we have this Butler-Vollmer description. So this is all things which we need to work on. There is a lot of understanding which needs to be generated in the next time. But it's a
Yes, thank you, Professor Thomas. And Professor Ahmed, and it seems that your mic is off if you want to continue.
Yes, thank you very much. It's indeed very complicated. It's the most complicated one to use solar energy at the interface or to use electrode very effectively. And this is a problem since the time where we attend the Gehrig talk and Tribuch talk about it. There is the whole school from United States like Bard. I think there are many researchers. I remember when I started my thesis in France about water splitting with titanium oxide. There are already in the literature a lot of publication about electron transfer and so on. That's how I come to know Tribuch in France, in CNRS, etc. And of course, do you think you have this? Of course, by the way, that's really a multidisciplinary research in the sense that chemists alone cannot resolve it. Physical chemists cannot resolve. There are many people they have to be together, and also material science. Material science is huge without really resolve the problem. And then there is one thing where Professor Tribuch always talk about it. We should invite him here to talk about this. He considers always transition metal chalcogenide, like ruthenium, like tungsten, like iron, where I worked also on. Do you think that the transition metal chalcogenide are the key to resolve this problem of catalysis for water splitting, or because it's create also defect this transition metal near the middle of the band gap? And do you think this defect are positive or negative for water splitting?
As I told, this was the important part which I always bring in. This is the point where I'm saying that the diffusion length, so in the absorber itself, this is the heart of the whole device, which is driving everything. If this stops, then everything stops. Even if the situation at the interface would be very good, if the heart is not any more working, it stops. So everything, the driving force is the photoabsorber. And the boundary condition of the photoabsorber is very clear. It needs to absorb light. Otherwise, there is no generation of everything, of free energy. And it needs to keep the free energy without losing it. And it would lose, for example, if the charge carriers would not arrive at the electrode and die before. So this is very clear. So what we need to make sure in any kind of photoabsorber is to keep this free energy, which is called the voltage in the semiconductor. And this people forget many times. In the heart, we need a very good photoabsorber. And if this photoabsorber is not fulfilling all boundary conditions, then it cannot work. And these transition metals, or metal semiconductor, this have, so far as I know, not sufficient properties so far to exactly do this. These two things could prevent this. Either the mobility is not good enough, if the charge carriers are too slow and die before, or if the lifetime is not enough. So if the lifetime is very low due to recombination losses, then it's also not possible. And for this, as far as I know, for this materials, semiconductors, which you have listed, I think there is always, so far, a severe problem with both the mobility and the lifetimes. So this is a point which needs to be solved. Otherwise, the heart is not working. And if the heart is not working, it does not work. So there's the so-called photoluminescence. All these photoabsorbers need to show enough photoluminescence so you can basically see it if they are good enough.
Okay, thank you. I think Ben Youssef.
Yes, Professor Ben Youssef, you can. Yes, Professor Ben Youssef. Professor Ben Youssef, you can. Start.
Thank you very much, Professor Hannappel, for this very nice talk and very instructive talk on photovoltaic and water splitting. I have one question about the way to design this and junction, because it seems that it's not easy to design material that have Fermi level higher than the first semiconductor one, band conduction, and lower than the band of the second one, or the P1 and N type second semiconductor. How to make this design easy for the criteria to show for the choice of the semiconductor? The two semiconductor for this heterojunction.
Yeah, it's a very good point also. Yes, indeed, the so-called charge selective contacts, traditionally we call it in the solar cell.
Professor.
I'm sorry, I was muted, I think. Professor Ben Youssef, I think there's background noise from your.
Yes.
Yeah,
now sorry. You can go ahead.
Yeah. So what I wanted to say is this is a very good question. This charge selective contacts, we have in any solar cell, we have these charge selective contacts very good. In any good solar cell, being it silicon or cadmium telluride or chalcopyrite solar cells or any very good solar cell, you always see that you have very good charge selective contacts. This is, for example, titanium dioxide, or this is other oxides in the different types for the cadmium telluride solar cell. And any thin film solar cell also with a very good performance, you always see that you have very good charge selective contacts. This can be many different materials. With exactly what you were saying, it needs to be the appropriate band offset, and either the conduction band or the valence band. But as we have many different good solar cells, you see that we also have many good charge selective contacts. It can be very different. Can be due to high doping, can be due to a higher band gap like titanium dioxide or other oxides. Could be also cadmium sulfide or many options. You see this in any concepts. I could now summarize all the different charge selective contacts, but we have very good ones, since we have very good solar cells. So, and this is an absolutely important point you are addressing.
Professor,
Now we cannot hear you.
your mic is closed if you want to say something. Your mic it is closed, Professor Ben Youssef.
Professor Ben Youssef, I think your micro was
you are muted.
But I think you were just...
Yes,
yeah.
now we can.
Thank you very much. Thank you very much, Professor Hannappel.
Thank you.
Pleasure.
Right. Any other questions or comments? Right. So I think Professor Thomas Hannappel, if you give us the conclusion to close the session, then I will move with Ahmed, Professor Ahmed, to finalize the things. Please, the floor with you.
Just thank you again. Just wanted to say that I appreciate the invitation very much, and thank you again for the invitation. It was a pleasure.
Thank you.
Thank you very much, Professor Hannappel. I think your contribution today for the opening series of seminar to the virtual university was excellent. I hope to have you every time to just to highlight the progress of your research and also in the field of green hydrogen using imitating the nature. Thank you again for your kind acceptance to our invitation, and thank to the whole audience. And I wish to everyone best wish, and maybe I will show you what we have for tomorrow if you are interested to come, or you invite your friend or your other student. So thank you so much.
You can just a reminder for tomorrow. It will be the last session.
Okay. Yes. So tomorrow we will have a talk. We'll have a talk in the afternoon at 2 p.m. Morocco time, and it's from Evan Gordon. He's the manager photovoltaic technology energy system at EMEC. It's I think in Belgium. He's also professor of digital photovoltaic at Detlef University of Technology, and by the way, he is also editor-in-chief of solar energy material and solar cells. And he's going to talk tomorrow about the whole status of crystalline silicon photovoltaic technology, which is his field where he is working. So that's one. So in the afternoon, in the morning at 11, I will also at 11 I will talk, and I think I have the same philosophy than Thomas Hannappel, where I always, since I come from the school or from Professor Tribute School, I always inspired by the nature, and therefore I will give a talk on photovoltaic, power to X, solar fuel, building integrated photovoltaic digitalization. So all what is can help the sustainable development, and just overview. Tomorrow is the last day of our series, so this talk will be really a general talk where we can see what is photovoltaic, what is power to X and fuel and solar fuel, what is building integrated photovoltaic, how far we can go, and also what the digitalization and industry 4.0 can bring to the manufacturing in photovoltaic, etc. And it will be at 11. My talk is at 11 a.m., not p.m. I did a small mistake here. This is 11 in the morning. And so you are welcome to also to this talk. And thank you very much.
Thank you.